In this video, we want to look at the parent functions for cosecant and secant. So in order to think of the graph of cosecant and cosecant, I would like to think back to the graphs of sine and cosine. The cosecant, remember, is the reciprocal of the sine, and the secant is the reciprocal of the cosine. So as I'm graphing, I want to think of those original functions. So I have my graph for sine up here. If I'm going to graph a cosecant, I want to start out with those original points. The sine of 0 was 0, the sine of pi over 2 was 1, the sine of pi was 0, the sine of 3 pi over 2 was negative 1, and the sine of 2 pi was 0. Now, when I go to flip, if I'm flipping 0, that does not exist. So my cosecant graph is going to have an asymptote on the x-axis. It's going to have another asymptote when I get to pi, and it's going to have another asymptote when I get to 2 pi, because all of those will have 0 on the bottom of a fraction, which doesn't exist. When I take the reciprocal of 1, it's still 1, and the reciprocal of negative 1 is still negative 1. So my points at pi over 2 and 3 pi over 2 are going to stay the same. Now, all my other values, if I were in here on this first arc of my sine curve, when I do the reciprocal of those, they become bigger. And what I have here for cosecant is an upward-facing u, and then on the negative point, I have a downward-facing u. But the period of this graph is still 2 pi, and I use the same points I used when I was plotting a sine curve. I just connect the points differently. Similar thing is going to happen when I go to do my secant. I'm going to plot my parent function for cosine. So I would start at a peak, go to the middle, go to a valley, go to the middle, and go back up to the top. Again, when the cosine is 0, so at x equals pi over 2, when I put that on the bottom of my fraction to make a secant, it's going to be undefined. And at 3 pi over 2, again, my secant is going to be undefined. Any of my peaks in my cosine graph would make upward-facing u's in my secant. Any valleys in my cosine graph would make downward-facing u's. So that's how I plot a secant curve. Realize, just like with sine and cosine, if I shift, I'm shifting this first point. So when I shift for a cosecant point, I'm going to start my shift with an asymptote. When I shift for a secant curve, my cosine would have been at a peak, so I'm going to start my secant curve at the bottom of a u when I shift. Okay, so here is a secant curve that we can go through all the steps to graph. Remember, just like sine and cosine, when I start out, I'm going to want this inside here in factored form, not the way it's currently written. So I would like the 1/2 to be separated and pulled out from the x. So I need to think of what's going to happen right there. Realize when I'm dividing out a half, I'm essentially doubling. So when I double minus pi over 5, that would be minus 2 pi over 5. Again, this is something we struggle with, so it's a good idea to double check. If I redistributed, I'd get 1/2 x, and then when I distribute over there, I'd have my 1/2 times my 2 pi over 5. That makes my 2 pi's reduce out and gives me the original problem that I had, so I know I factored correctly. So I'm graphing my secant curve, but I'm going to think cosine right now, because secant is the reciprocal of cosine. So what do I know? I know I have a 5 out in front. Well, that means the amplitude of my graph is 5. But that 5 is also negative, so the negative out in front tells me I'm also going to flip vertically. What else do I know? I have a 1/2 as my stretcher on the inside. That's going to affect my period. The normal period for a secant curve or a cosine curve would be 2 pi. I need to do the opposite of whatever this says because it's on the inside. So rather than half, I'll double, and my period is really 4 pi. My phase shift is going to be 2 pi over 5, and that's going to go to the right because subtraction on the inside moves me to the right. On the end, I have a plus 8, so that's going to move my midline up to y equals 8. So let's see what I need to put on here. I'm going to start with my x-axis. And I know that my first point is going to be at 2 pi over 5. So the first point I'm marking on my graph is at positive 2 pi over 5. In order to do 2 full cycles, I need 9 marks. To figure out how far apart I need to make those marks, I need to think about my graph. The cosine curve is going to take 4 pi to complete. Now that takes 4 pi to complete 4 pieces of the graph, so my quarter of a cycle would be a quarter of that period, 4 pi, and a quarter of 4 pi is pi. This number is how far apart I'm going to make my marks. So if I need to add pi to get to my next mark, and I'm at 2/5, I would like to get a common denominator, so I'm going to think of that as 5/5 to get my next mark. So 2/5 plus 5/5 is 7/5, plus another 5/5 is 12/5, plus another 5/5 is 17/5, then 22/5, then 27/5, then 32/5, then 37/5, and finally, what's that, 42/5? Okay, I don't have a y-axis on there yet. Since this mark at 2/5 was positive, I'm just going to come to the left of that to make my y-axis. The middle of my graph is at y equals 8. So I'm going to come up here in the middle of my graph and put on a mark at y equals 8. From there, I needed to go an amplitude of 5. So I'm going up 5 and down 5. 8 plus 5 is 13, and 8 minus 5 is 3. So those are the marks I need on my graph. Again, we know I like to make highlighter marks along my graph so that I can tell exactly where my function is oscillating back and forth between. Now I'm going to plot my points. I'm thinking of the cosine curve. Normally, the first point for a cosine curve would be up at the top of the cosine curve, but I've got a flip out in front with my negative. So instead of being up at the peak for my cosine curve, my first point is going to be down there at the valley. Then I would go up, middle, I would go from the bottom to the middle, to a peak, to the middle, to the bottom, to the middle, to a peak, to the middle, to the bottom. I know if I've done 2 full cycles, I should end where I started, and both of those points were at the bottom, so that looks pretty good to me. Wherever my cosine curve hit the midline, so it hit the midline right here at 7 pi over 5. It hit the midline right here at 17 pi over 5. If the cosine were hitting the midline, the secant is going to be undefined, so all of these points are going to give me vertical asymptotes. Then I know anywhere I was at a valley, I make an upside down U. Anywhere I was at a peak for my cosine, I make a right side up U. I'm going to get close to my asymptotes. If my asymptotes are real far apart, I don't want to make super skinny little u's. I want to make them actually go near the asymptote because that's my border for my function. All right, so here's my graph for my secant curve. Let's talk about the domain and range of this thing. My cosecant and my secant curve have a whole series of places that they're not allowed to be. Anywhere I had an asymptote, so it's 7 pi over 5, 17 pi over 5, 27 pi over 5, 37 pi over 5, this graph is not going to exist. So I need to come up with a way to write x can't be equal to any of those points. I'm going to start out here and I'm going to say x can be any real number because I'm allowed to be all sorts of values in between those numbers. And then I'm going to put a new variable in there. I like to call it k, and I'm going to say k is an element of the integers, which are z, because of the Germans. And then now I'm going to say, here's what's happening. I'm going to say x cannot be equal to 7 pi over 5 because that was one of my asymptotes. I always pick the first positive one when I'm writing this explanation. Now I need to come up with a way to say, now I can't also be 17 pi over 5 or 27 pi over 5 or 37 pi over 5. Well, all of those asymptotes are 10 pi over 5 apart. I went from 7 to 17 to 27 to 37. So each time to get from one asymptote to the next, I'm adding 10 fifths. Well, 10 fifths reduces to 2 pi. So I need to say I'm not allowed to be my original asymptote, which was 7 pi over 5, plus 2 pi times k. That means any multiple of 2 pi could be added or subtracted to my 7 pi over 5. If I needed to write this out in sort of a general description, what I'm doing here is I'm saying x is a real, k is an integer. I need to say k is an integer because I can't put in here something like a half. That won't work. I have to add whole numbers of 2 pi's. Okay, so k is an integer, and then I'm going to say x cannot be equal to, and then I'm going to just write any asymptote right down. Once I have one of my asymptotes down, then I'm going to add to that whatever the distance between my asymptotes is, and that distance is going to be multiplied by k, this variable I wrote up here. Now, some textbooks use n instead of k. It really doesn't matter which letter you choose. I choose k to emphasize that it could be either a positive or a negative constant number rather than just a natural number that n usually is. Okay, so this formula right here will work to write any periodic functions domain that has asymptotes. Okay, the range of this function. I could start out with y as an element of the reals. I don't have to. I need to go from all of my peaks down. So I would be y is less than or equal to 3, or I could also be any of my valleys up. So y could be greater than or equal to positive 13. I have to write that word or in between there because I can't be both things. I have to be either less than 3 or greater than 13, but none of the spots in between, which is where the cosine or sine would have gone. If I wanted to write this in interval notation, I could say from negative infinity to 3, 3 would get a bracket because I equal it, then I would put a u for union, and then 13 would get a bracket because I equal it, and it would go up to infinity. Remember, both of my infinities need parentheses because I never equal them. To write the domain in interval notation pretty much requires the same type of expression as we had right here. So it's all reals except those x values. What if this graph had said cosecant instead? I would have done all the exact same work up to now. The only difference will come when I start putting the points on. When I'm doing a cosecant curve, I want to think sine. Sine starts in the middle of a curl. So my sine of 2 pi over 5 would have been in the midline. Now a normal sine curve starts in the middle and then goes up from there, but I had my vertical flip. So instead my next point would be the down point, then the middle, up, middle, down, middle, up, middle. Rather than connect them with my wave shape, I'm going to do the same thing I did for secant. Everywhere the sine curve's in the middle, my cosecant curve is going to have an asymptote. So all of these midline points, I draw asymptotes for. Then I do just like before. Any bottoms will turn into downward facing U's, and any peaks will turn into upward facing U's. Let's go ahead and write the domain for this one also. So to write my domain, I say x is an element of the reals, and k is an element of the integers, the z. X cannot be equal to, I need to pick an asymptote. My first asymptote was 2 pi over 5. Then I'm going to say plus, and now I need to tell you how far we go to get to the next asymptote. Well, to get from 2 pi over 5 to 12 pi over 5, I added 10 fifths, or 2 pi again. And then that would get a k with it to say I keep adding multiples of 2 pi over and over again to get to the next asymptote. So the range of this function would be just like it was for the secant curve. Y is less than or equal to 3, or y is greater than or equal to 13. We need to know those parent functions and make sure we think about whether we're graphing a cosecant and plotting a sine curve, or whether we're graphing a secant curve and plotting a cosine curve first.